Okay, I want to show you a way that you can estimate the delta H or enthalpy change of a reaction by using what's called heats of formation or enthalpies of formation. Enthalpies of formation are simply the energy required to produce a compound of some sort from its initial element. So as I bring this together, how much energy is released or required to produce this item, this chemical? What you will tend to find is that if you have fairly strong bonds and so forth, generally means it's got a high heat of formation, enthalpy of formation, which means when it comes together it's going to release a lot of energy and generally be somewhat stable. The lower that number, generally the more potential energy there is in the compound. So let me show you how this would work, and you need tables for these, and my students get a reference packet. You can find these in other locations, but basically what you're going to do is you're going to look and say what is the heat of formation of carbon dioxide, and you're going to multiply that by the number of carbon dioxides, in this case 4, and then you're going to add that to 6 times the heat of formation of water. And again, in my tables I list water heats of formation for gas, liquid, solid, and so forth, or gas and liquid. So you have to make sure you're using the correct number. And then you subtract from that the energy required to produce the reactants. And so what ends up happening is you're going to take 2 times the heat of formation of ethane, ethane, and turns out here this is 0. Elements in their natural state are considered to have a heat of formation of 0. So what I'm going to do is I'm going to take 4 times the carbon dioxide number, 4 times, and if you look in your table you can see the carbon dioxide is negative 393.5. And I'm going to add that to 6 times the heat of formation of liquid water, which is negative 285.8. Okay, so I've gotten this whole thing together is going to produce it's going to do the heat of formation of all of my products. And from that I subtract the heat of formation of my reactants. So I look up and I say, well, what is ethane? Ethane is negative 84.7, and I've got 2 of them. So I'm going to do 2 times negative 84.7. By the way, notice that is a fairly small number, and that shows there's some energy, there's some potential here, whereas these are greater numbers, these are a little bit more stable. And then to that, of course, I would add on the reactant side 7 times my heat of formation of oxygen, which is 0. And again, as I was saying, elements in their natural state have a heat of formation of 0. So basically what I'm going to do now is bring these numbers together. 4 times this is negative 1574. I'm going to add that to the product of these numbers, which is negative 1714.8. And then I'm going to subtract from that basically 2 times negative 84.7, which is negative 169.4. So then I add these numbers, I get negative 3288.8, and I subtract negative 169.4, which is the same as adding it, and I get negative 3119.4 kilojoules. Makes sense. I'm burning a compound. I'm going from my reactants down to my products. Okay, these are more stable. My CO2 and H2O are more stable than my reactants. So as I go through that, you would expect energy to be released. And again, things like ethane have a lot of stored energy in them, a lot more potential, whereas the products, carbon dioxide and water, are a lot more stable. So the delta H in this case would be that negative 3119.4 kilojoules if I were to go through this reaction. So again, you're always going to take your products minus your reactants. And if I have less potential energy here than here, as I go this way, these are more unstable, this is a little more stable, more potential energy, less potential energy. So what ends up happening is I have a situation where the difference, as I go to this more stable state, I'm going to release that excess energy.